Hello class, welcome again for the mechanics recitation sessions. This is week 4. This week we will have 5 different questions, and let's get started with the first one, 0.73. Here we have a dome, and it is located below the water surface as shown here, and this is our dome. And we need to determine the magnitude and sign of the force components needed to hold the dome in place and the line of action of the horizontal component of force. Here, y1 is 1 meter and y2 is 2 meters. And we are assuming a 10 degree Celsius temperature. Okay, so let's get started with what we need to get in this question. So according to the question, we need to find horizontal force and its line of action. Let me say line of action. So we can say we will have FH. And this is for the second part of the question. And for the first part, it says we need to hold the dome in place. So this means that we need to apply an equilibrium so that this dome will be held in this place. In other words, it means buoyancy force should be equal to vertical force, or it should be equal to weight of this dome. So here we can say that we have FB, which is buoyancy, and to keep it fixed at this level, we will have F vertical. So let's first find FH, which is horizontal force. So FH is actually simpler because it is just average pressure times area. And in other words, it is specific weight times depth of centroid times area. So it will be equal to, and let me write the specific weight from table 8.5. So for this temperature, the water specific weight is equal to this value. So it will be equal to 9,810 times, let's find depth of centroid. So we can make a sign here. So this is actually centroid. And we need to find the distance from the water surface to the centroid. So this value was 1 meter. And here we have 2 meters. So since this will be the diameter of this dome, the entire distance is 2 meters, and this half distance will be 1 meter. So we can say this is 1 and this is also 1. So when we look at the water surface and the centroid, we can say that the distance is 2 meters. So H centroid will be 2 meters. And for the area, we need to consider a full circle area instead of half, because here it looks like a half circle, but instead we need to consider a full circle. And to explain that, for example, we can assume that we are standing in front of this circle and we are using a flashlight. So even though this looks like half circle, we will see a full circle on the wall. So this means that this is actually our projected area. This is what we call that. So regardless of it is half or full, we will take full circle area. And for the full circle, of course, it is pi r square, which is radius square. And we have pi times 1 square. And from there, we will get 61,640 Newton, which is equal to 61.64 kilonewton. So with that, we calculated the horizontal force. Okay, now let's focus on this first part of the question, which we need to find the magnitude and sign of the first component needed to hold the dome in place. So actually, this horizontal force will not impact this dome. The only important component will be vertical forces. So we will have FB, which is vertical force, and we will have buoyancy force. So actually, when we say FB, this is buoyancy force. In other words, it is equal to weight of the displaced fluid. And as mentioned, we need to hold the dome in place so that FB should be equal to FV. And here's FB will be actually equal to weight of this dome. And when we say weight, it is specific weight times volume. In other words, we will have volume of circle as 4/3 pi r cubic. However, here we need to be careful about the circle. On the contrary of this horizontal force, we need to use half circle. Because here it was a projected area, but here we need to use actual area, which is here, because we are considering the actual displaced volume. So in this case, the displaced volume will be here. So this means we have a half circle here. So we will have half volume. Because, for example, if a body is submerged, the displaced volume will be the portion of that volume. So that we have this half circle. And let's continue. FB will be equal to half circle's volume times specific weight. So we have 1/2 I. The radius is 1 meter, as we calculated earlier. Times specific weight of watch. So FV vertical force will be equal to 20,550, or it is equal to 20.6 kilonewton. So let me summarize what we did here. Here, since the question said we need to hold the dome in place, we need to have all vertical forces equal to each other. I mean, all opposite forces should be equal to each other. So we will have a buoyancy force and we will have vertical force. Since we have upward buoyancy force and we have weight of this dome. They should be equal to each other so that we can balance the upward force with this downward force. So to get that, we need to find the weight of this shape. And since it is half circle, the displaced weight will be half circle's volume, so that we obtained vertical force. Now in the third step, let's focus on the line of action of horizontal component. As we did in previous weeks, we are going to use this equation, which is center of pressure is equal to depth of centroid, or distance from water surface to the centroid, plus inertia over distance times area. So this gives 2 plus I 1 meter 4 over 4, and this is coming from inertia of circle over, we have 2 meters times the area of circle, pi 1 meter square. So from here, we will get 2.125 meters. So the pressure of center, the difference between the pressure of center and the depth of centroid will be 0.125 meters. So we can see that here, actually. This was the centroid, and the center of pressure will be around here. Let me use another color. And this distance is 0.125 meters. In the second question, we have a submerged spherical steel buoy that is 1.2 meters in diameter and weighs 1,800 Newton, and it will be anchored in salt water 50 meters below the surface. We need to find the weight of scrap iron that should be sealed inside the buoy in order that the force on its anchor chain will not exceed 5 kilonewton. So first, write what we have. We have weight of this spherical steel buoy. So let me write everything on the shape. So we have weight of this buoy, which is W, and it is equal to 1.8 thousand Newton. Also, the question says that it will be anchored in salt water 50 meters below the surface. So this distance is 50 meters. And the diameter is 1.2 meters. So this distance will be 1.2 meters. And the anchor chain will not exceed 5 kilonewton. so that we will have a tension here. So we should fix it at 5,000 Newton. So we used downward force here because this anchor chain will try to pull this steel buoy to downward, while we will have an upward force, which is FB, buoyancy force. So briefly, this buoyancy force will try to uh, pull this buoy to the surface, while this anchor chain will try to pull it to downward, so that we will have this opposite force. So from table 8.4, the specific weight of seawater, salt water, is equal to 1,007 Newton cubic meter. And the question wants us to find the weight of scrap iron inside of this buoy. So let me use another color. As you can see, we have some scrap irons like these ones. So we need to find a weight of these scrap irons. So let's write W scrap. Okay, so first of all, we need to write buoyancy force equation. FP is equal to specific weight times the displaced volume. And we have the value of specific weight times volume. Let me write it again. So we have times pi times the radius is 0.6. So we will have 0.6 cubic 0.6. We need to write equilibrium because we say that the total vertical forces are 0. Because this object is floating, and it means it is in a state of static equilibrium. So there is no acceleration, so there is no up or down movement. Therefore, total vertical forces are 0. And let's write all vertical forces. We have FB, which is buoyancy force. On the opposite side, we have weight of this entire steel. We have T, which is coming from tension of anchor chain, which tries to pull this steel to the bottom. And we have scrap iron weight, and we are using it as additional weight to keep this steel floating without movement, without any movement. So weight of scrap. In the first step, we actually calculated buoyancy force. So it is 911 Newton is equal to 1.8 thousand Newton, which is coming from the weight of boy. So P should be equal 5 kilonewton. Plus we have weight of scrap. And the scrap will be equal to 2,310 Newton. Okay, this is question 0.85. To what depth D, which is here, will this rectangular block with density of 0.75 times that of water float in this two liquid reservoir? So we need to find this depth so that this block will be floating. And we have density of block, which is 0.75 of times of density of water. So in the question, it is said that the block will be floating so that we are going to have equilibrium, which means that it will be in a state of static equilibrium, so it is not moving up or down. So all acting forces will be zero. Here we will have two different solutions for this question. One with electrostatic pressure or using buoyancy force. And let me get started with the first one. Here, of course, we have weight of this block, and we will have a pressure at the bottom of the block, so that we can say there will be an upward force. This is because we have force, we have pressure at the bottom, and there will be a pressure force which is upward because this block should float. So we will have upward pressure force. So let me write everything we have. We have weight of block, and this is downward, and we can see negative sign. And we have upward buoyancy pressure force. Sorry. So let's say pressure force on bottom of block. And this should be zero. For the weight, we can use specific weight of block times volume plus pressure at bottom times area equal to zero. So we have weight of the block and we have pressure force on the bottom of block. So let's go with the first one. Here we have width of 6L and we have height of 3L, but we are missing the third dimension. So we are missing actually deep. We are missing depth. So we can assume the bottom of this block is square. So we have a depth 6L with 6L and height 3L. Here you can also use any other term because eventually it will be cancelled out. And we are assuming 6L because it is not stated in the question. So you can either assume 1 meter or it's up to you. So since the density of this block is 0.75 times of water, we can also use same specific weight. So let's write 0.75 specific weight of water times we have 6L square, which is B times B, or the width times depth times height to calculate the volume. And this will be minus. Plus, we have pressure, and pressure is specific weight times depth. So we will have two different pressures because let me that we have this part of the block and we have this part of the block. So as you can see, we have two different fluids here, so that we need to consider this part and this part separately. So for the first part, let's write the equation. It is specific weight of water times area. So here the area is, we have L, we have 6L times 6L. So we can actually write the area of bottom, which is 6L times 6L, outside of these parentheses, because it will be same for this part as well. Plus, now focus on the second block, second part. So here the height is Y. So it will be Y times, here we have another fluid, as I mentioned, and it is 1.2. So its specific weight will be 1.2 specific weight of water. And as I mentioned, this is common for both of these sections because they have the same bottom width and depth. Here we can get Y is equal to 1.04 L. So D will be equal to Y plus L, because when we check the figure, we have D is equal to L plus Y. So D will be equal to 2.04. So this was the first possible solution for this question. And we use hydrostatic pressure on the bottom of the block. So for the second solution, which we use buoyancy force, we need to pay attention to this info. So if we have partially submerged block or any shape, we need to use volume of that portion. So what does it mean? Here, as you can see, we have two different blocks and two different fluids. So we are going to need to use a portion of this fluid, and then we are going to use this submerged portion of that fluid. And for buoyancy, since this will be floating, the weight of this block should be equal. Let me use another color. This time it should equal the buoyancy force, the total buoyancy force. So when we say total buoyancy force, we will have two different buoyancy force. So let's say this is first and this is the second one. And if you remember, in the first solution, we used the pressure force on the bottom of block, and it was equal to weight of this block. This time we keep the weight of block same, because eventually these vertical forces should be equal. So it will not make any difference if you use buoyancy force of these two sections, or if you use pressure at the bottom, pressure force at the bottom. So now we are at the second solution, and let's see what buoyancy forces we have for this one and for the second one. So first, let me write the weight should be equal to buoyancy force, because this is floating. So the weight of the shape will be, we have 6L, and we can still keep using this depth as 6L. It wasn't given, but we can assume it is 6L. So in that case, we will have 36L square times this distance of the shape, which is 3L. So this is actually the volume of entire block times we have specific weight of water. And in total, this gives, weight of entire block. Actually, let me write this here. And this is going to be equal to buoyancy force of first block. Let's see what we have. So we will have 6L, we will have L, and we will have a depth, which is also 6L. So let me write this. So this is general buoyancy equation, specific weight times area. So let's say this is first one. We have specific weight of water. Its specific gravity is 0, so we will just keep it as it is, times the width is 6L, the depth is 6L, times L, because of this distance in this block. And for the second one, let's see what we have. Again, we have 6L with 6L depth and Y distance. So this distance is Y. So the height will be Y. And let me write 6L times 6L times Y. However, here we need to pay attention to specific gravity, which is 1.2. So let's say 1.2. Let me move this here. 1.2 specific weight of water. And this is the entire total value is 0. And here I need to fix this, because in the question, the density of block was 0.75 times that of water. So instead of using that, we need to use 0.75 with the grade of water. As we did in the previous solution, we can just cancel these specific weights out. And after some minor calculations again, we can get L plus 1.2 y is equal to 2.25 L. 1.2 y is 1.25 L. Y is equal to 1.04 L, which makes D was equal to y plus L. And from here, D is 2.004 L. This is question 4.14. Water flows in the passage shown, and if the flow rate is decreasing with time, the flow is classified as steady, unsteady, uniform, or non-uniform, and we need to select all that apply. So when we have steady flow, it means that the velocity or flow rate at each location is constant with time. So we can say V over time is equal to 0. Or since this is flow rate, we have Q over T is also 0. And when we have unsteady flow, it means that we have changing velocity and other flow properties. So since this is changing with time, we can say that this is unsteady flow. And if we look at if it is uniform or non-uniform, uniform means the flow properties are constant in magnitude and direction along a streamline at each time. So if we have uniform flow, we should have streamlines which are parallel to each other. But here, as you can see, we have changing streamlines, and these are not parallel to each other. So this means that the velocity changes along a streamline in magnitude, direction, or both of them. Therefore, we can see that this channel is changing. So we have narrow at the beginning and we have wider channel sections. This means that we have non-uniform flow. Or in other words, velocity over streamline change is not 0, which means we have changing flow properties along this streamline. Okay, we are finishing the recitation with this last question, 4.17. Here we need to classify each of the following as one-dimensional, two-dimensional, or three-dimensional flow. And here we have three different figures, and these are coming from your textbooks. So this represents 1D, this is 2D, and this is 3D. Let me explain what these dimensions mean briefly. So when we have 1D, the velocity depends on only one spatial dimension, namely the radius r. So we have r. So it's just following this streamline. And the second one is two-dimensional flow. And here the flow can move forward, backward, or up and down simultaneously. So for example, we have this one, and we can up or down movement of this in this flow, so that it will be two-dimensional. So for this one, we are using x and y dimensions. And for the third one, we will have again x and y dimensions. So this means we have a flow which is moving forward or back or up. For example, let's say this is moving forward. It has up and down movements. And also, this time we have sideways, or in other words, I mean that the cross-section area is expanding in the flow direction. So as we can see, we have an expansion in this cross-section. So in addition to these ups and forwards, this time we can have sideways movements because our cross-section area is expanding and it's changing, so that we will have three-dimensional flow here. So let's see what flow types we have. The first one is water flow over the crest of a long spillway of a dam. So let's say we have this kind of dam. And we have this water. Let's say we have water racing to this level, and then it is spilling. So here, as you see, we have a flow that follows that streamline. And now we will have vertical flow chains. So this means that we have a two-dimensional flow here. For the second one, flow in a straight horizontal pipe. And actually, it is directly mentioning figure A, which shows a horizontal pipe. So here, the flow is just following this straight line, so that we will have one-dimensional flow. In the C, flow in a constant diameter pipeline that follows the contour of the ground in hilly country. So here, the important information is it is a constant diameter, so that, for example, we have this pipe. Its diameter is constant. But this pipe is following the contour. So for example, let's say it is something like that. So again, we will have this flow that follows that streamline. It looks like we have two-dimensional flow, but it is not the correct assumption, because it is still following, and it is still following the pipe, and it is still within this pipe, so that even though the pipe is changing its shape, changing its path, the flow in the pipe is still following the streamline. Therefore, we will say it is 1D. For D, we have airflow from a slit in a plate at the end of a large rectangular duct. So this means that it actually directly mentioning rectangular duct, which is 2D. But let me explain. So let's say we have airflow, and this velocity change as the air moves away from the plate and spreads out. For example, let's say at the end of large rectangular duct, this spreads out. But it is not changing along this duct because the diameter is constant. It is not like 3D, because if it was 3D, we would have this expansion, or it would get narrower, so that we would have a third dimension. But here, actually, let me correct this. We have this one directional flow, and it can go up and down because it is spreading out. But it is not changing along this duct, because unlike 3D, we have constant. So airflow past an automobile and airflow past a house, these are 3D because, for example, let's say we have this car, and let's say we have this house, and when we have water around this house or automobile. They can actually move in this streamline direction. It can go around this car or house, and in the car it can get these sides because these shapes are not constant, so that we can have a flow in this direction. It can go up and down. For example, let's say in this house, and since the constant is not the shape is not constant. Uh, for example, let's say we have something like this. The flow will also change in this direction. So water is coming from here. It can go up, which makes the second direction, second dimension. And inside of it, it can also spread out like this, or same for the house. It can go up, it can go right, it can go in the depth of house, so that these are 3D. And finally, we have water flow past a pipe that is laid normal to the floor across the bottom of a wide rectangular channel. So, for example, we have this channel and we have this pipe. Once water comes, they will move around the pipe, but however, they are still following the same streamline. They are not, how can I say? They're just coming from the sides of the pipe. You can think it as like a traffic. So we have three lines. We have one car here. We have car two here. We have car three here. And let's say we have some object in this way. This will go this way. Even though the second car merges with the first lane, it is still following one direction. They are not going up or they are not going doing something else. So this is the first direction. And we will have a second direction here. We also have water here, and since it is going across the bottom, this water should go up to pass this pipe. So this creates a second line. So basically, this will be 2D.